Hello, you beautiful people. So today is our last lecture. So it's not really the last lecture, but the last worksheet that I want to present to you. And today it's about reactor sizing in case you don't have isothermal conditions, but if you have changing temperature. So we want to look at the example from last week. We still have an equilibrium reaction, so A is in equilibrium with B. We use the same Arrhenius parameters like last week, so you know this already, but this time I gave you the reaction enthalpy, so 75.6 kilojoule per mole, and this should be assumed as constant. Then we have a different starting concentration, so this time it's 4 kilomole per cubic meter and not 1 kilomole per cubic meters. We have a mole flow of 1000 moles per minute, so 1 kilomole per minute, and the heat capacity, so this is a new quantity, so it's tilde Cp. This is 1050 joule per moles Kelvin. I show you what this Cp tilde, what this is all about. And we want to play around with this equilibrium reaction in different reactors and different temperature conditions. So let's go back to last week. Last week I showed you how to get these diagrams. So here you have the temperature, there you have the conversion, and then we plotted in this diagram, we plotted constant values, we plotted lines for constant values of the reaction rate. So here the units are skipped so that the legend is a little bit smaller. The units are still mole per liter minute. And what you can see here is that, for example, if you look at this line here, there you have a reaction rate of 3 moles per liter in minutes, and you can see if the temperature is increased, then your conversion will go up. And then if you go close to the equilibrium, then it will go down again. And if you say, okay, let's try to find the highest reaction rate that you can get for a certain value of your conversion. So let's say, what is it, like 45, a conversion of 45%. Then the highest reaction rate you can have is the value of 3. If you go in this direction, then your reaction rate will decrease, because you are close to equilibrium. This means your reaction rate is going down. If you go in this direction at a certain conversion, then your reaction rate goes down, because your temperature is too low, and so by the Arrhenius equation you can see that your rate constant is decreasing. And since this point here is always the best or the highest reaction rate that you can have for a certain conversion, this is a special path, and this is the path of the maximum rates. In the last slide I called, in the last worksheet, I called it locus of maximum reaction rates. So, and with this knowledge, if we have the best reactor that we might have, and we can adjust the temperature very, very precisely, then it's the best idea to just proceed with the temperature on this curve of maximum reaction rate for a given conversion. So here in the worksheet I gave you some restrictions. I said, okay, the maximum temperature should be about 95 degrees Celsius. So we cannot go all the way along the locus of maximum, but so here it's 95 degrees. We start here, and then we can use this turn here, and then go up to our desired conversion of 80%. So we want to have a conversion of 80%. I think I gave it to you in the last example, even if the starting concentration was different, but we had the same target conversion of 80%. Okay, so now we know how our perfect temperature would look like for this reaction. And yeah, how can you, or with what reactors can you achieve this temperature profile? So basically it could be a batch reactor or it could be a plug flow reactor. And here I choose, for the next slide, I choose the plug flow reactor. So we want to have just very simple plug flow reactor, no big thing, but we need to have a heat transfer about across the boundary of the plug flow reactor. And with this we can say, okay, we start with 95 degrees and then the temperature has to go down, and at the outlet of the plug flow reactor we need a temperature of 62 degrees. Okay, and what can we do with this information now? Okay, let's say we start here with, let's say, okay, we want to have this point here as our first value. Then we can say, okay, I want to note down my reaction rate R, and I want to have the corresponding value of my conversion. So here the yellow line is the reaction rate of 15, and my conversion here is about 2%, so 0.02. Okay, then next point, what can we see here? The reaction rate now is 10. You just look it up in the legend. So R is 10, and here it's about 17%. So, whoops. And then again, next thing is the blue line. This is 5. And here you can see this is rather close to 34. What did I wrote down? Yes. 34. And so on. So basically you can do it for every point here where you have the different reaction rate, and then you can create a new diagram that could look like this. So here at the conversion of 2%, we have a reaction rate of 15. So this is the first value here. Then the next one is 10 and 17% conversion. So 17% conversion is here, and then you have a reaction rate of 10. So not very complicated. And then you go down to a conversion of 80%, where you have a reaction rate of 0.4. So let's have a look here. The yellow line, there it's 0.4. Okay, but if you want to calculate your residence time, then it's CA0 times the integral 0 to your outlet conversion times 1 over R dxR. So, and if you look here, so we don't have the inverted reaction rate on the x-axis and the y-axis, but we have here the reaction rate. So the x-axis is fine. So we just need to transform this. So it means we have to transform R to 1 over R. This means this 10 here becomes 0.1, and the 5 becomes 0.2, and so on. And if we do it like this, then our diagram would look like this. So here we have 1 over R, and our conversion is here. And as I wrote to you on the last slide, so our residence time is tau is CA0 times integral 1 to 1.8 1 over R dxa. So, and what you now have to do is you have to find the area below this curve here. And what you can do is, so you can just play around by judging by eye. You can say, okay, let's assume oops, just wanted to erase it. Okay. So what you can do is, I think it's not that, or I think it's possible. If you say, okay, what do you have to make sure? The most or the easiest thing is to draw in something like a rectangle, and this means you have to find the value here, and the area above this must be the same area as this one here. So these two areas must be the same. And I think just by using your engineering knowledge or just your experience, I think it should be possible for you to end up with a value of 0. Value of between 0.4 and 0.6. So if you would say, or if you say, okay, I'm not getting 0.5, which is the correct value, but if you would say, okay, maybe the line is somewhere here, then you would say, okay, this area here should be the same as this. So this should be the same as this. I think if you go below this value, then you will see it doesn't make sense. And the same applies for a value of 0.6. If you go above it, then it's very clear to see that it's not very meaningful to have it like this. Okay. So here the correct value is 0.51. How can you get the correct value? For this you can use it's not that easy to pronounce, trapezoidal rule, I would say. Okay, what does it mean? I think you know it from CVT1. If you have something like this, if you have here 1 over r and here you have your xa, basically like this, and then you have some values here and the next one is here, and you want to know the area, then you can say, okay, basically this is something like a trapeze, and the area of this one is, so let's call this here I, and this is I plus 1. So then the area here is so AI is 1 over r at the position I plus 1 over r plus I. This you have to divide by 2, so then you would transfer it to the mean rectangle, and you have to multiply this by the difference of your two conversions. So this is xa I plus 1 minus xa I. And to get the whole integral, so if you want to know your integral 0 to 0.8 1 over r dx a, then this is the same nearly as your sum of all i's from your ai's. We used this in CVT1. No, we used it in CVT2. What is the difference between the situation that we have here and the situation in CVT2? In CVT2 we had equidistant, or we had the distance between our point was all the same. And here is the problem, the step size here. So for example, the distance here is much bigger than the distance here. So your delta XA, or your delta in your conversion, has always different values, and that's why you cannot just simply use the formula of I showed to you in C4T2, but you have to calculate it like this. So if you want to do it, then it's so with MATLAB or Excel or whatever, it's no problem. And if you do it, then you will end up with a value of 0. So this one with the value of 0.408. So this is from the calculated from the trapeze rule, and with this trapezoidal rule I calculated this mean value of 0.51. So if you want to do it in a simple way, then you can just say, okay, my area here, this is just a rectangle, this side is 0.8, this side is 0.51, and then you end up with an area of 0.408. And then your volume, your reactor volume for this plug flow reactor with the optimal temperature profile is just the volume times the volume is the volume flow times the concentration, and this is our inlet mole flow of component A, and then you have to multiply it by this integral. So in your calculations or in the example values there, the mole flow was given 1000 mole per minute. Then you have your integral value here, and then you end up with a plug flow reactor volume of 408 liters. So it's less than half a cubic meter. Okay, so this is in case where you have your perfect temperature control. So perfect temperature control is not so easy to achieve, especially if you have reactions in the gas phase. So heat transfer in the gas phase is always difficult to achieve. You have low heat transfer values, that's why it's not that easy. But what is rather easy to achieve is adiabatic operation. So for this we need some simplifications. So let's say we have our equilibrium reaction in any kind of reactor. We send in a mole flow of component A to the inlet, and we say we have a heat capacity that is constant, we have a total mole flow that is constant. For the total mole flow you also have to take care of your solvents or inert gases or inert materials or whatsoever. So your total mole flow could be much higher than the mole flow of your component A. And we say your reaction enthalpy should also be constant. And then at the outlet you can calculate what's coming out of the reactor if you know your conversion. And if you just do a simple enthalpy balance, then you can say, okay, if I have an endothermic reaction, so this is negative, and you know your inlet mole flow, and you know your conversion inside the reactor, so this is rather the heat that is released, and the heat which is released, this should lead to a temperature increase. And the temperature increase can be calculated if you know the total volume flow through the reactor, if you know the heat capacity, and then here is your temperature difference. So let's have a look at the signs. So exothermic reaction, this means this should be negative. Here you have a minus, then this is a positive value, and this would lead to a temperature increase. So your outlet temperature is higher than your inlet temperature. And yeah, so if you can rearrange it, you can say, okay, I write it here like this. Our conversion is minus the ratio of the mole flows times the heat capacity. So the heat capacity of your total mole flow. And yeah, then here you have the ratio of your temperature increase divided by the enthalpy of reaction, or reaction enthalpy. And just to avoid much writing, you can introduce a new parameter where you say, okay, I introduced this new Cp tilde, and this is just the ratio of your total mole flow to your inlet mole flow of component A times the heat capacity of your total flow. Okay, this means if you have a lot of solvent, or if you have a lot of inert material in this reactor, then this value here would become rather large. If you have, if you only add your component A to your reactor, then this would be the same as the total mole flow, and then this is just this ratio here is just 1. So you can write it like this, or you can also say, if I want to calculate my temperature difference, so the temperature increase between outlet and inlet, this is just your conversion times the reaction enthalpy divided by this new Cp tilde. Okay, what does it mean? If you want to plot it, then so let's say, okay, here you have your temperature. Maybe let's say here you have your inlet temperature, T0, and here you have your conversion, XA, so 0 going to 1. Then what does it mean? So if you look at this, so for example, if you say I want to know what would be my outlet temperature if I have 100% conversion. So 100% conversion means, okay, I go to XA1, and then you have a straight line in between. This means you have it like this, and this you can calculate by minus delta RH divided by Cp tilde. Okay, so and here again you can see if you have a rather low value of your Cp tilde, this would be Cp tilde low, or reaction rate, reaction enthalpy is high, then your curve would look like this. If you have a lot of inert material, let me use a different color. So if you have something like this, then your Cp tilde would be high, or your reaction enthalpy would be low. So this would result in a curve like this. Okay, so if you have adiabatic operation, this means depending on your conversion, your temperature would behave like this. So, and what you have to do now, let's start with the adiabatic operation of a continuously stirred tank reactor. What you have to do now is, okay, you have to find out what is your enthalpy balance. So in the worksheet I call this line here, I always call enthalpy balance, just that you know what I mean with this expression. Okay, for the example reaction that we have here, you can put in the values. So your Cp tilde was given to 1050 joule per mole Kelvin. Your reaction enthalpy was given to 75.6 kilojoule per mole. So you have a delta T max of 72 Kelvin, and this is at XA, so at 100% conversion. So, and with this, it's rather easy to construct your enthalpy balance. So let's say we start at 20 degrees Celsius, doesn't matter where we start, somewhere where we can easily calculate it. And we know, okay, my delta T max for 100% conversion is 72 Kelvin. This means if I start with 20 degrees and my delta T is 72 Kelvin, then my outlet temperature should be something like 92 degrees Celsius. And then your enthalpy balance would look, I almost got to the correct point. Okay, now it's better. So this would be again the line for the enthalpy balance. Okay. But if you look at this right now, if you want to go to 80% conversion, so then with the inlet temperature of 20 degrees, you will never ever reach it, because 80% is then out of it's on the right side of your equilibrium curve, so it's not possible to get there. Okay. And now we just have to find out, so what's the best inlet temperature to operate a continuously stirred tank reactor. So we want to have a conversion of 80%, and we want to have the highest reaction rate that is possible inside of the continuously stirred tank reactor. And you know already, this is exactly this point here. So we want to go to this point, and we know how our enthalpy balance looks like. So what we have to do right now is we just have to do a parallel shift of this curve. So we want to end here, and we know the slope of our curve, so we just have to go this way. So this is parallel shift, and then we can say, okay, so I know the exact value, so this is 4.4 degrees Celsius as our inlet temperature, and then everything is fine. Okay, how would it look like? So now we would send our feed with the inlet temperature of 4.4 degrees Celsius to our continuously stirred tank reactor. But since the continuously stirred tank reactor is perfectly mixed, inside the reactor we always, in any position, we find a conversion of 80%, we find a temperature of 62 degrees Celsius, and everywhere inside the reactor we have a reaction rate of 0.4. So this is the reaction rate at which the continuously stirred tank reactor operates. Okay, so basically it's here again, same picture. So here 4.4 degrees Celsius, and this is 62 degrees Celsius, and we have a conversion of 80%. Okay, of course you can also calculate it. If you rearrange the formula, you can write it down like this. 62 degrees Celsius we found here in our diagram. Then we have a conversion of 80%. We know our values here, and then you can calculate the 4.4 degrees Celsius as inlet temperature. And so the main question was, what is the reactor size for a continuously stirred tank reactor? And this is very easy to calculate. So I think you remember the worksheet on the continuously stirred tank reactor. So this is just the inlet mole flow times the conversion divided by the reaction rate. So we know the mole flow is 1000 mole per minute, conversion is 80%, the reaction rate here is 0.4 mole per liter minutes, and then you end up with a volume of 2000 liters, and this is nearly 5 times the volume of the optimal path. So your temperature control, well, with a good temperature control, you can really minimize your reactor size. Okay, this was for the continuously stirred tank reactor. Next question is, what would be the size of a plug flow reactor with adiabatic operation? And here we start with a bad choice. So we start here with the inlet temperature of 4.4 degrees Celsius. So this is basically the same line as we had for the continuously stirred tank reactor. So with this, our enthalpy line would stay the same. It would look like this, but this is not the best choice. So T0 is not the best choice. You will do the best choice as your homework. But this is just, I want to show you how to do it, and then you can transfer it in your homework. Okay, what does it mean? We start here, and for a plug flow reactor, your temperature and your conversion are changing all along the way through the plug flow reactor. This means you enter with a temperature here, for example, of 4.4 degrees Celsius, and you have a conversion of 0, and then you proceed along this line here, and then you will end up here with a conversion of 80% and a temperature of 62 degrees. And here, in every intersection, so for example here you can say, okay, why is it not the... Okay, so let's say here, at this point you can say, okay, for a temperature of, what is it, 10 degrees Celsius, I have a reaction rate inside the reactor of 0.12, and I have a conversion of 8%. So, and now it's again, you look at all the intersections. So you're looking for the intersection of your enthalpy balance and your reaction rate. So for example, you do it here and you do it here, and again you can see that here you have your maximum. So this is our max. The maximum reaction rate is 0.4 moles per liter minute. Mole per liter minute. So this is here, and then you can see, okay, my reaction rate again is decreasing, and then at the outlet of my reactor I will have a conversion of 80% and a reaction rate of, what is it, blue one, it's again 0.4. Okay, and then I think you know what you have to do. You have to use all this data, and then you can create with it 1/r XA plot. And this is what I have done for you on the next slide. So this means our 1/r XA diagram looks like this. And yeah, what you have to do is you have to find a rectangle. You have to find a rectangle. So this one that has the same area, as the area below the blue curve, and this means again that this area should be the same size as the red area, and I did it again with the trapezoidal rule, and then I found, okay, the good value here is, the best value here is a size of 3.79 for 1/r, and here again you have 0.8 and with this it's rather easy to calculate your area. Okay, and then you can say then you can calculate your volume of your adiabatic plug flow reactor. But so that you can check it in the worksheet. There I gave you the values. But what I want to do is I want to show you how you can find a better value. What you have to do for this, let's say red. If you start here and then you would go like this up to 80%, then you will see, okay, if I start with 20 degrees Celsius at the inlet, then I will never reach 80% conversion because I'm on the right side of the equilibrium, so it's not possible. But what you could do is maybe go to a value that looks like this. So you are here, you are rather close to equilibrium, but you are not on the equilibrium line. If you are on the equilibrium line, this would mean your reactor size has to become infinitesimal or very big. Okay, and what's the advantage of this? If you look at this, then you can see, okay, now you have intersections of your line here with much higher reaction rates. So for example, your maximum reaction rate is close to 1 mole per liter minute, and then here you are going down. So with this, you have in this area you have higher reaction rates. And for your overall reactor size, this is quite positive. So if we look again, if we have a look at this graph here, then if you enter with a higher inlet temperature, then you would have lower values here. So I don't know the exact values, but it should look like this. So you are much lower here, and then just at the end here you are going to really low values. So here you have reaction rate of, let's say, 0.2 or even lower, and this means you have a very steep increase at the end of it. But if you say, okay, I just need the area below this curve here, then I think it's clear to see that the red area here is much lower, or is lower. It's not much lower, but it's lower than the area that we had before. And this is what you shall do as a homework. I just gave you 2 calculations. So A is determine the reactor volume PFR of an adiabatic PFR with an inlet temperature of 16 degrees. So this is the best value. Use the diagram given in figure 8. So this is basically a diagram that looks like this. To determine the values of the reaction rates are at different temperature conversions, and construct the 1/RXA diagram. So this is basically just what I showed you here. You have to do it with the inlet temperature of 16 degrees and calculate the reactor volume. And B is use the same 1/RXA diagram to determine the reactor volume of a recycle reactor with a recycle ratio of R is equal to 0.82. Okay, so since we are running a little bit out of time, it's the deadline for this is Wednesday the 17th. I hope that I will finish the solution to this and upload it in the morning of June 18th. So this should be Thursday, and then you have 4 days left to prepare everything for the exam, which takes place at the 22nd of June. Okay, all the best. Hope this video was a little bit helpful to better understand the worksheet. And yeah, so if you are bored, then you can color this slide here. Okay, yeah, goodbye.